Okay, coming up here any minute, we've got Inigo Muguruza Guenaga from Erle, is going to give us a short talk about microcontroller meta cross compilation.
Okay, thank you very much. Yeah, I'm Inigo. I'm just a hardware engineer at Robotics, and today I'm going to show you just some work we have done with INRIA Research Institute. I think one of the authors, Loic, is somewhere over here, right, Loic? Yeah, and we just collaborate to bring ROS2 to microcontroller level. So just you might just wonder if it's difficult just to fit ROS2 into a tiny devices. I mean, if you just, some of them, I don't know how many of you just work under microcontrollers here? Just some? Yeah, okay, I see. So you just may know that these kind of systems are like pretty just difficult to use because you have to just really just learn a lot about how they work. You need to get into really like deep level, like getting these registers. And if you just use a hardware tensor layer, just you really need to know how they're working. So we believe that ROS2 users should just abstract for this just say difficulty and should just smoothly code ROS2 code into microcontrollers. So we just joined forces with INRIA, and we are just here presenting a meta cross compilation approach that we came up with, and that I want just to present here. So I want to just talk about previously about the some implementations already done under microcontrollers under ROS. And also we have seen that in the last weeks new approaches have arisen. And then afterwards I want to just talk about this meta cross compilation we have came up with and just show you some examples. Okay, so I guess that ROS in microcontrollers is not a new thing, right? We have seen many packages and tools already in the last years, and one of the most famous one is ROS Serial, that is based on ROS1, that they want to just to bring tiny microcontrollers like the Arduino-like, that they have just a few Ks of RAM available, and normally just use they have like a 8-bit processor, microcontroller processor, and they just want to hook it up to ROS. So they were basically using just serial communication for doing that. They were implementing a header where you can implement a node where this tiny device could subscribe, publish using using a proxy that is normally a computer that is connected to this microcontroller that able to just to integrate into the ROS world. Then afterwards, we have seen that this approach has been also translated to additional microcontrollers like Texas Instrument and Tensi ones. Also, when ROS2 development was kicked off, also we saw some efforts. One of those is just reflected in ROS2 embedded NATEX repository that was made by my colleague Victor. And there they tried to squeeze a complete DDS implementation, I think, into microcontrollers. He was using a pretty big microcontroller. He was using an STM32F4 that has 256 Ks of RAM, so it's a rather big one. And they needed the additional external RAM, so just imagine how complex could be just putting such a big thing into a microcontroller. And also, the OSRF also made some effort re-implementing all the RTPS implementation, and they just came up with free RTPS. And while also I was just preparing this presentation, I just noticed that also some other people like Politecnico di Milano also they brought also ROS1 to microcontrollers, as for example the package Microsnode, where they were using tvOS with a lightweighted IP to bring them. And lately we have seen also some more efforts to just bring ROS2 into microcontrollers. Some of those, one of them is just the Opera project we are involved with some partners like Proxima, Bosch, Piap. And we want, in this approach, we want to include a complete XRCE DDS implementation to microcontrollers and just integrate them in ROS2 world. And we are also just checking the ROS serial approach and how we can reuse this in ROS2. Okay, so let's go to just analyzing which are the problems where you can find porting microcontrollers to ROS2. One of the main one is the RAM size. I mean, obviously, you cannot take whole ROS2 code and squeeze it in just a device that has a few Ks of RAM. Another problems you can face also is that ROS2 uses heavily C++ new standards like the 14.1. And normally, these kind of standards are not supported by microcontroller toolchains. So this is also a big problem. And also that each RTOS also has a really different compilation process and procedures, and normally are not compatible with ROS2. So you will have 3 ways to go to just support ROS2 microcontrollers. One of those would be just to add support under ROS2 for each microcontroller or RTOS. That could be like a really harsh task. And or just getting this RTOS you want to use and this microcontroller under just, let's say, compiling with ROS2 toolchain. That could be also harsh. And we just follow a third approach that we think is more pragmatic and more useful, that we have called it like a meta cross compiler. That what we do essentially is we take ROS2 source code, and in the first step we just translate into a RTOS dependent source code, like an application. And then afterwards we use a native RTOS toolchain just to compile and create a binary where just the microcontroller is able to execute. So putting that into a graph, it will just look like this one. So in the left side, you can see how a regular ROS2 package is just composed of, like source files and CMake list and so on. And you will use just Ament to compile that. Or right now it's Colcon. When we did this prototype, we were using Ament. You will just use Ament or Colcon just to create a binary that you are able to execute under a microprocessor. And the idea we came up with is just using this two-step compilation process, where we create first a new Ament file, where we just import all the code that is related to the microcontroller. So the user will just code the ROS2 code that he wants to use in the microcontroller, and thanks to this Ament file, we just translate that into a RTOS-specific code, source code. And then afterwards, we just use the regular toolchain that the RTOS are using just to finally have a final binary that the microcontroller is able to run. Okay. So this is I'm showing some amend to NATEX file we have created to create an NATEX RTOS specific implementation, and just some configuration of the stack, about how it's called the application and so on. And using this, we will just create a source code that is really, it's NATEX source code that you will just use to compile afterwards using the makefile system that NATEX uses. And we made 2 tests. I want to highlight here that I'm showing just 2 microcontroller boards, but you could just have as many as you want, because I mean each RTOS has maybe different board support, so you could just reproduce this in different boards. INRIA was focused on Riot real-time operating system, and they replaced the DDS middleware, and they just put NDN on that, and they also reworked they remade the RCLC layer just to be compatible. So they end up having just a test where they were using a ARM Cortex M0 Plus that has just 32 Ks of RAM using the complete stack. As from Air Robotics, we did the same test using NATEX, and we end up having the same test using just a bigger board. So we just really validate that this approach is feasible. Okay. You have there the links if you want to consult the work we have done. And what I want just to conclude is that I think that there is a huge interest in porting ROS2 into microcontrollers, and that you are just everyone welcome to contribute. So if you are interested, you can drop me an email, or otherwise we are going to have a meeting at lunchtime. So just come with us and just let's talk. Okay. Thanks.
Thank you for that. We've probably got time for maybe one question.
No one?
So actually I have a question. One of the, I often see companies deciding to use something more special purpose when they go down to a very small microcontroller. There's this concern that a general purpose framework like ROS2, that somehow you lose too much in efficiency or overhead. What's your opinion on that?
Yeah, we are actually looking like different approaches to support ROS2. That's why I just brought this ros-i approach, because we think that for really like tiny microcontrollers, maybe it makes sense just to use this kind of approach. But if we have like a larger ones, maybe we can just fit a complete stack of ROS. So we are still like in a moment that we want to make some tests on that and see which kind of environment we have or we could have in the future. So we can just have like really tiny microcontrollers that maybe they just publish some sensor values, or we can just have more complex things going on there.